make an innocuous assumption. I mean, we will keep on making such assumptions as we go along in this course, and you must have already made such assumptions in your previous courses, that we have to, we compare with the classical case, and now we have to define what is the classical case. The classical limit of quantum mechanics is a slippery thing, but in this case it is not so slippery. This is what I am trying to convince you, that we have chosen a given orthogonal set, and as we have discussed before, that whenever we have a set of distinguishable states in the physical description of the problem, then in the mathematical description we choose them, we represent them as orthogonal states. Now, of course, in the Hilbert space there are many orthogonal bases. Which one do I choose? That may also be restricted in the actual physical problem when you consider it. So, I mean, dead and live cats are orthogonal states, but dead plus live and dead minus live, these are also orthogonal states. And these two orthogonal states we have not seen in practice. So, but in the quantum description, these two are just two bases. They have equivalent status. So, this 0, 1, although I have allowed them to be an arbitrary orthogonal basis, it may actually be further restricted. But I am not putting that restriction.
So further restriction meaning like getting a classical meaning out of it.
Getting a classical meaning out of it. There are further problems that have not been solved for the classical limit of the quantum mechanics. Yes, how do I get Newton's equations out of a Schrodinger equation? This is not understood clearly. And there are some people who have worked on this and they have some answers, but these are still controversial. But in this case, we don't have such a problem. We just have a basis. We have, in the quantum case, we will consider even superpositions of these things. But in the classical case, we have chosen a basis. We haven't said which basis. At least a basis, one basis. We fixed it and focus on it. Yeah? In the classical case.
So this could very well have been plus or minus.
In principle. The problem will still go. But then you have, if 0 and 1 represent looking at the top and the bottom, I mean, you are plus meaning you are looking at the top plus the bottom together, and this doesn't have a meaning classical. This is the point that I am getting at. So, what I am trying to say is that with a single use of the black box, it is not possible to find whether the fair or biased. Yes, you check that if I look at only one of these lines, I get this either F0 or F0 bar or F1 or F1 bar. From that I cannot find out what is F0 and F1. Yes? Yes, if I know F0, I don't know what is F1. If I know F1 bar, I don't know what is the other one. From F1 bar I can find F1 but not F0. With two uses, if I use two lines, any two lines, I will be able to find it. for example, by using A and C, no sorry, I made a mistake. Not any two lines, I have to choose the line. So if you use this and this, you won't be able to find out because they are the same information. But you choose the options in the usual way that you see whether, so this and this or this and this will work, yeah, or this and this will work. There are many options. So for example, using this A and C, you will be able to find it. We can find out whether the coin is fair or biased. So the question now is, can quantum mechanics help in finding out whether the coin is fair or biased by using UF ones. So we had stated the problem in terms of the coin. Now to deal with the quantum case, we have stated the same problem in terms of this unitary operator. Yeah? So we have a black box and we are allowed to run it once. In the classical case, you won't find out whether the coin is fair or biased. We will see that in the quantum case you can. So we will now give the quantum algorithm. Quantum algorithm runs as follows. There will be 2 pages of algebra. Very simple. Step 1, prepare x, y. You remember that the our black box requires an input, yes? So and those inputs were x and y. So we prepare that x, y as 0. Classical basis. Apply Hadamard to both. You know what is the Hadamard gate? Yes. So it takes 0 to 0 plus 1 and 1 to 0 minus 1. Takes to, it is considered to be one of the most quantum gates. So there are this quantumness of gates one can consider, and this you see that you go from one basis to something that is a superposition. There are many superpositions, yes. So one could have considered, so this 0, this plus and minus are 0 plus 1 by root 2 and the minus is this. But there are many others that are like this. We have chosen this. The reason is that these are the so-called mutually unbiased bases. Yes, so mutually unbiased bases mean that you choose a basis and you go to another basis, then every element of this basis and every element of this basis, if you take the inner product and the modulus, it will give you the maximum value, which is 1 by root t. Once more. So you choose a basis in some Hilbert space, d dimensions, another basis in the same Hilbert space, d dimensions. These are both orthonormal bases. Then these two are called MUBs, mutually unbiased. Is it? Mutually unbiased, right? Forgot the name. I'm trying to call it maximally unbiased. Is it called? It's also maximally unbiased. But I forgot what is the name. But it's also maximally unbiased. I'll tell you why. I forgot about the name. But the purpose is that, I mean, when I have a basis, you have to think of that I will do a measurement of that finally. And when I do that measurement, I should get the maximal possible information out of it. Now, if I do a measurement in one basis and I choose another basis that is slightly away, I will get a little bit more information. So I should go the maximum possible direction away. Now, I mean, it's not clear how to go in that direction. And this is one way to see that it is maximal. This, for all j, is 1 over root t, for all I. So as an aside, let me tell you, so both of these are orthonormal sets in orthonormal bases in CD. For a given basis, there always exists one mutually unbiased basis. So in every dimension, you can find at least two. You just take the Fourier inverse of it, and you will get a Fourier transform of it. The finite Fourier transform, you will get the one MUB. So two MUBs are there in every dimension. There's a conjecture that you will be able to find out d plus 1 MUBs in every dimension. It has been proven for prime power dimensions only, not in others. So 6, for dimension 6, we don't know whether there are, so 6 is the first non-prime power dimension. We don't know whether there are 7. No, 4 is prime power, yes, 2 square.
Powers of prime are
Power, for every power of prime or a prime, we know the answer. For that, it was proven by
people haven't explicitly checked.
it's not easy to check explicitly, I mean numerically.
No, 0, 1, 2, 3, 4, 5. Write down a 7
No,
basis.
there is an infinite, the parameter space is
Parameter
infinite. Parameter space is infinite. I mean, parameter space is finite dimensional, but there are the parameters are themselves continuous. So this has not been proven as yet. Wooters in 80s, I think, I forgot the date, proved the thing for, and then the same result, this prime power dimension, was given a simpler proof, or maybe a separate proof, by Shomshubro Bandyopadhyay, who is now in Bose Institute. He gave a separate proof of the same problem, but still it didn't solve the non-prime power dimension.
For 2 dimensions, at least it's like the basis of sigma and sigma.
Yeah, x, y, z. In 2 dimensions, it's very easy. So, and these MUBs come up in many different problems like state estimation, in eavesdropping strategies, and many other things. Okay, so what I want to say is that this Hagemann gate takes you from one basis to its MUB. So we apply Hagemann to both, so that this becomes plus, this becomes minus, is these two are created. And then we feed it to the black box, the UF. Apply UF to plus minus. Yes. So we'll now find out what is UF plus minus. We'll write it explicitly. Well, there's a kits and there's a root 2 and root 2 that comes here. There are kits here and there's a tensor product here. I'm not writing all that. This is assumed to be linear. UF is 0, 0, 0, 1, there's a minus sign, and then there's a 1, 0 with a plus sign, and there's a 1, 1 with a minus sign. You understand this notation here? This is an operator that is acting on a tensor product of two kits. Now you go to our definition of the UF that we wrote a few boards before. It will be 0 F0 minus 0, I'm putting a comma for the tensor product, 1 plus F0, see whether I have done it correctly, plus 1 F1 minus 1 F1. Yes. These classes are the binary additions. So this thing is actually F0 bar. Yes, you have added 1. So this is an F0 bar. And this is an F1 bar. Yes. Then I can take 0 common, 0 ket as common, and inside I have F0 minus F0 bar, and then the same thing here, but 1 I take outside, and I have F1 minus F1 bar. Fine up to you. If the coin is fair, F0 is not equal to F1, which implies F0 equal to F1 bar. Yes. This is not equal to this, there has to be the other one. This is either 0 or 1, yes? And also F0 bar to F1, and you take bar on both sides. If the coin is biased, F0 is F1, which implies that F0 bar is F1 bar, yes? Now come here. So, if the coin is fair, is the top option, the state is come here. This is 0, and this is F0 minus F0 bar, and this can be written as F1 bar minus F1, yes? Because F0 is F1 bar and F0 bar is F1, yes? So I replace these things here. And this I keep as it is, the same thing. But now you see that this thing and this thing are the same thing except for a sign change. So you have a minus half, 0 minus 1, and F1 minus F1 bar. Yes? This was the general case. This is the case when the coin is fair. Now, and if the coin is biased, this we start with the same thing. This is equal to this, and in this case you can check that this is by just putting it here. Okay. So these are the two options. This one and this one. This one and this one. Any questions? So we had done up to 3 points in the algorithm, yes. We had already 3 steps. This is what we were doing in the 3rd step. We come to the 4th step. Apply Adamat to the first qubit. If the coin is fair, the resulting state at the first qubit, so there were 2 inputs and 2 outputs here. The top one at the output is a 1, yes. This is the case when the coin is fair. I apply the 0 minus 1. Now if you apply 0 minus Adamat on the 0 minus 1, it gives you a 1. Because 0 becomes 0 plus 1 and 1 becomes 0 minus 1, and you add them, you get a 1. And if the coin is biased, the first qubit is a 0. This is the output of the first qubit. You take this goes to 0 plus 1, this goes to 0 minus 1, so this becomes a 0. So the final circuit is you start with a 0 and a 1. This was the first step. We apply Adamat gates on both. Yes. This was the second step. And the third step, we apply the UF. And the fourth step, we apply At the fourth step, we apply the Adamada operator. And here, we put some detector. So this we haven't even mentioned at the last step. So this is detector measuring in the sigma z basis, in the 0, 1 basis. And this part is thrown away. The important thing is that we have used the black box once. In the bottom. So of course you realize that although the black box is used once, what has happened is that in that single run, it has evaluated F0, F1 and everything. Yes? So because of the existence of quantum superpositions, you can feed a quantum machine with a superposed state. So in the classical case, the options were you either given 0 or the 1, and then you get the answer of what happens to the 0 and what happens to the 1. But in the quantum case, you can put in both the things at the same time, and you get a single answer. But in the single answer, it's a superposition of those F0 and F1. And in some cases, the values of the evaluations of F that are done inside that superposition can be used to go beyond the classical case, as in this case. Yes? Remember that we have not evaluated F twice. The machine has given you a single answer. You have run the machine only once, and in that same run, because there are superposed queries, it gave you superposed answers. And from that, we have been able to go beyond the classical case. So this has a name to it. It's called quantum parallelism. So we will see this quantum parallelism in many ways in all these algorithms and error correction. So, yes, Tim.
So, when we were considering the classical case, when we were giving, say, 0, 0 and 0, 1, so here, like, 0 and 0 correspond to looking at the top of the coin twice, right?
Yes, so you have to remember that we first, to sort of motivate the problem, we considered the problem with coins, but then we changed the problem and used the black box. So it means, looking at the top of the coin and bottom of the coin in this changed case corresponds to feeding the thing with a 0, 0 or a 0, 1 or a 1, 0 or a 1, 1. There are these 4 options of the inputs.
Sir,
So if I look at a coin, how will I know, how will I fix X and Y? If I give a coin.
No. So looking at the top of the coin is a value of X.
Yeah.
Looking at the bottom of the coin is other value of X. That is the input. And at the output, you look at the coin and get a value. That value is the output. Get the point?
No. So what are X and Y corresponding to a coin?
So there were these 2 problems. Yes, one is the problem which was the coin, and we were tossing the coin and we were trying to find out what side it is. Now with a coin you can't have superposed queries, so we have to changed that format to a situation where we have kets and bras. Yes, I mean we can superpose and so on. So we have gone to a situation where, I mean, in principle you can think of this plus as a query where you look at the top as well as the bottom. I mean, as well in a superposed sense. But yes.
So the state we are getting for the biased and the unbiased case,
Mm-hmm.
like they are also mutually orthogonal.
Yeah, yeah.
So does that have a significance? Like we can distinguish them completely?
Exactly. So if you don't, you can put a detector here that will measure in the sigma x basis. This will do the job. So suppose you are here, you don't apply the Hadamard. At this point, you use a detector. You dump here, and here you apply a detector that measures in sigma x. So this is the sigma x basis, yes? This and this. And this will give you the answer. The point is that for quantum circuits, it is important that you begin in the computational basis and at the end you measure in the computational basis. Otherwise, you tend to you can be misled by the amount of resources that you require. So measuring in the sigma x basis, in some technologies it may be done directly, but in many technologies it is actually, theoretically you may write you are measuring in x, but in the laboratory you actually have sigma z and you put a Hadamard in front of it. Now every item of machine that you put in the the is a new resource. It has noise in itself. It requires some time to implement and all this. So the usual strategy, the usual way to write quantum circuits is to begin in the Z basis and at the end measure in the Z basis. If you require, so for example here, you could have said that you begin with a plus and a minus, yes? Was it a plus and a minus or minus and a plus? It's actually a plus and a minus. This is Hadamard, this is plus and a minus. This is Hadamard on 0, 1, it gives you plus. So you could have said you remove the first two step, this middle step, and you begin with a plus and a minus. It's true, if some technology lets you do that, that's fine. But if you write this on paper and go to the experimentalist, for many technologies, they will actually do this and implement this. This is different from actually this. Theoretically is not, but technically it is. Experimentally it is.
Sir, what is this like? The concept of the coin was just an example of like the biased coin, whether the coin. So what does this algorithm like? What is it actually used for?
So as of now, it's not useful yet.
Oh.
So you will see that this idea will be able lead you to factorization. It is the same quantum parallelism that is used for the Schroeder algorithm. And in this case, you actually know the answer in the classical case. That in the classical case, you require two queries, and in the quantum case, you require a single query. In the Schroeder, this is not the case. You know the answer in the quantum case, you don't know the answer in the classical case. You believe that it is super polynomial. So that is also, this gives you an example where there is a gap between classical and quantum.
So even though there are like measurement is happening just once, but in between there are certain let's say operations we have to do.
Exactly.
So,
Yeah.
so it's not like completely untedious compared to the classical case where we had to measure 2 times.
Exactly.
Just in
Yeah. So
measurement
we are
is-
measuring only once here. That is true. So in the classical case, you also have to. So this, you see, in this state preparation and measurement and these type of things are considered to be trivial in the classical case. That you have only one basis. Whereas in the quantum case, even state preparation takes some time. But we have made a difference between the classical and quantum case by being able to run this UF only once, where in the classical case you have to run it twice. This is the difference.
Sir, running UF twice in the classical case means we are giving two different inputs, like either 0, 0 and
Yeah, you have to choose it carefully. Yeah.
So giving one input is looking at the top and the bottom. Like 0 is the top, 1 is the bottom.
Exactly.
So in the classical case, if we are giving two different inputs, doesn't it mean that we are looking at the coin 4 times?
No. We are only we will only use it for the two line. I mean
Okay,
this is something that you have written on paper. But when you will do the experiment, you will do the experiment only for this line and this line.
Yeah. So in that
So
case, this line means I'm looking at the top and the top.
Y isn't the coin. Instead of X coin.
So this is the part that represents the coin, but you have to remember that here coin means the state 0, 0 is looking at the top and 1, 0 is looking at the bottom. Because you're not using these other two lines. So you use only this.
Okay.
There is not an exact one-to-one. There is not an exact one-to-one relation between the coin. There will be, of course, be. So to make the problem more specific, we have chosen this black box model. So the coin thing is for the motivation to why should this be called as a quantum coin problem. So to compare, you have to use just the black box in the classical and the quantum case. Anything else?